Okay. Good morning. So we'll be going over the practice problems. We will not be going over all of them because, as I mentioned in bold red text, this is a lot longer than your exam will be. We will not be able to go over the answers to all of these in class today, but you also have your recitation tomorrow to go over more of them. I will instead highlight the things that I think are most important. And the solutions to this will all go out on Friday after your recitation. So you will have access to the full set of solutions. Let's actually start with the exam logistics. This is a 75-minute class period. You will have a 70-minute exam. It will start at 10 after the hour, right? So that all of our wandering through sleet, snow, and whatever is or is not gracing our Tuesday morning will not overly impede us. Standard, grid version to see whose test was where. And let's start with problem number 1. Understanding performance. So some of these things are going to be review in terms of the skills, but I think 1A is the exemplar of what you should look at here. How do we apply the same things we were used to, the execution time equation, Amdahl's law, et cetera, to relating new features that we have actually learned about? Right. So if I want to compare performance and do speed up, I just need to know the execution time for the two things and compute speed up. Great. How do I do execution time? Well, I use the execution time equation. Right. That has not changed. Right. Even if one of them is VLIW, the execution time equation is pretty straightforward. Right. I have some number of instructions. Each instruction takes some number of cycles. There is some, clock time. I multiply those together, I get time. Right. So all I need to do is relate how I would put in the properties of some VLIW processor into that model. And VLIW makes this very easy because VLIW, a bundle is just like an instruction. Right? If I do bundles, per cycle instead of instructions per cycle, or sorry, cycles per bundle instead of cycles per instruction, right? It would look exactly the same. Right. So all that you actually need to do is figure out how to relate new things we're learning, this, plug and chug, and the rest is algebra. Right. There's some other things you can pull away from this as well. Right. If I do tell you that the VLIW processor has 2 instruction bundles, then the amount of useful work per instruction bundle is on average is bounded from epsilon to 2, right? So you can also look at what the best case speed up this thing could possibly, provide us. What's the best case speed up that you get? If your speed up is 2b over 3, where b is the number of instructions per bundle, number of original scalar instructions per bundle, what is your best case speed up? S is equal to this. If you follow it all the way around. If S is 2b over 3, and b is at most 2, it should be pretty straightforward that our maximum speed up is 4/3. Right. Okay. So I think this is a very good one to ponder. Again, ponder what is actually being asked and measured. Right. Yes, we're asking you to review and some basic formula, but really this is mostly can you relate them, the old and the new. Okay. So the rest of these are less interesting, so I'll go over them a little faster. But you do want to go back perhaps and look at the slides from recitation on the sort of extended Amdahl's law, where you have the Amdahl was an optimist and Amdahl was a pessimist. Right. So this is again mostly about generalizing. Right. Can you move away from the world where all pipelines are exactly 5 stages, have exactly the same functionality, everything is MIPS, there's only one processor we're trying to make work, right? We're using the simplest, versions of all of the formulas we can throw, and we look at trying to stretch that a little bit, right? So for instance, here we say, okay, what if, right, rather than just having a portion that an optimization is applied to, right, this optimization affects different portions of the program differently. Right. Other than that, straightforward Amdahls. Okay. This one, again, looking at how you can transform something that seems to be talking about CPI actually back into an Amdahl's law equation effectively. Right, so can you move and integrate the different formula that we have learned for performance analysis? All right, so if I tell you that you've got a processor with no cache and some fixed time amount memory, right, and then we're going to change the frequency, you should know that changing the frequency did not affect your memory, i.e. there's a portion of your program that was unaffected by an optimization and a portion that was. This sounds like an Amdahl's law question. All you have to do now is try to figure out as to write it in terms of an affected and unaffected portion based on the fact that the information you were given was about CPI. Right? You can do it thusly. You can say I have execution time is instructions times, well, 1 times C, but I can split it into an affected and unaffected portion, right? Times the clock time. And I can, then just multiply those out. And now I have 2 times, one of which is affected and one of which is not. Apply an optimization. Bob's your uncle. All right. Some of these require more algebra to solve than you would actually have on the exam. Don't actually bother solving this for K. That is left as an exercise to the reader with too much time on their hands. If you can set this part up, you're good to go. Okay. E is a little bit of a, I won't call it a trick question, because it's not. But it's about more remembering what these values that I'm telling you actually mean. Okay. If I have 2 machines, one's x86, one's ARM, so they are very different ISAs. I have a program P compiled for X as CPI of Y and for A as CPI of Z. The frequency of A is 1.25 times that of X. And the instruction count of running on P on X is 0.8x, that of running P on A. What information we need for some program Q? So the important thing here is that all these stats here, other than the frequency, have everything to do with P and not the hardware. The only thing we learned about the hardware was this, right? Everything else is a function of the program you were actually running. So if I measure, how fast Angry Birds runs on your phone, and I want to learn from that, how quickly you are going to be able to run ChatGPT, the answer is, I have no idea, right? You've measured the wrong thing, right? If I measure a few thousand programs and I get an average between these 2 ISAs, maybe I get something here, but if I measure 1 program, no, it tells me nothing about Q. Right? I still need all these other pieces of information. Okay, here is an Amdahl was an Optimist version of a question. Right? It's not too bad. So here we're asking about the break-even point. Right? That's pretty easy. I have my old time, I have my new time, I set them equal. That'll be the break-even point. So what was my old time? My old time was, well, the original portions of the program. A%, which is parallelizable, B%, which is not. Right, that's all of my time. Here you're told what the value of n is, right? So you just can say that this is speed up proportional to n. This doesn't get sped up at all, and this has some overhead that rises as a function of n. Hopefully you can do the log base 2 of 4 without a calculator or an abacus, or a lookup table, And then again, the rest of this is pretty straightforward. Okay, and again, G is literally just an even further generalization of exactly 1C. So we will not go over it in the interests of time. Okay. So there is a trade-off in any problem that actually asks you to do something, compute something, in giving you enough information that you can actually have a well-defined answer, and also in trying to figure out which parts of this were the most germane, right? So if I just jump actually all the way to the end here, if all I want to do is express my throughput improvement as a function of latency improvement, so latency improvement, also known as speed up, right? And if I'm running 2 copies of something and they're a factor of s faster, then it should be pretty obvious without doing any further introspection or math or application of exterior knowledge or previous knowledge, that my throughput improvement is 2s. Right? If my improvement in unit time is a factor of s, and my improvement in the number of things I'm doing is 2, then my throughput improvement is 2s. Okay. Now, what is s? Okay, there you actually need to go and apply a little bit of computer architecture knowledge. Okay. But again, do make sure that you answer what the question actually asks. All right. Okay. Let's go through. Any questions so far? Again, those are all review. Good. Okay. So let's maybe zoom. Bloop. What if we wanted to be smaller? Let's be smaller. Better. How's the text visibility in the back? You see it? Yes? No? There are lots of seats in the front. Let me see if I can make this a little bigger here. Better? Good enough? So the process of figuring out where the control flow blocks are, right, where the basic blocks are, is very simple. I will walk through this and you will go, oh, it's very simple. Okay, we're going to begin at a label. All right, so we begin at the beginning. A very good place to start. Right? Don't worry, I will not spontaneously burst into song yet. Okay, so we're going to start at abalone. And we are going to say, okay, our basic block is going to start from instruction 1, and it will continue until I hit another entry point. How do I know if I hit another entry point? There'll be a label, right? Why? Because I am not a cruel and unusual person who is going to have you do computed jumps to figure out where your entry points are randomly in the middle of your code, right? That's not a good test question. That's just how you actually go find bugs in your analysis in your compiler if you assumed that everything was nicely labeled. Okay, so we're going to go until we hit either a control instruction or another entry point, because basic blocks are single entry, single exit. We're just going to walk straight down until we hit BEQ on instruction 5 and say, well, okay, at 5, we go one of 2 places. So that's the end of that basic block. Okay, so where do we go from instruction 5? Well, we either go to instruction 6. That's the beginning of some basic block, or we jump to Barnacle at instruction 8. Okay. Now, if we went to instruction 6, 6 continues down to just instruction 7, which is another control operation. Again, could you have cases where your jumps are actually considered straight line code because nothing else can actually possibly reach that label? Yes. Will you see that in this? No. So treat your jumps the same way you treat branches, even though they only go to one place. They are the end of your basic block. Right? Without loss of generality, it's still a valid optimization. Okay. Now, we know that this is going to skip check was at 10, right? So will this graph remain planar? I don't know. I didn't do that in advance. So meanwhile, if we didn't go to 10, then at instruction 8, we go to 8 and then 9. And then we can't, 10 can only not be in 2 basic blocks. 10 is a point, which is a label for something else. So if we included, even though this is a linear straight line run of code, that can't be part of the same basic block because, well, that would not be single entry anymore. Right? If I put 10 over here, I could enter in multiple places in this basic block. So no, it doesn't look like that. It looks like that. Right? Okay, now 10, right? Immediately after 10 is a label. So the end of the basic block starting with 10 is 10. So actually the same is also going to be true here for 11 and 12. Right? Those are single instruction basic blocks. So 10 does in fact always go to 11, but there are other things that can also go there as well. Okay, so 11 goes either to 12 or to 25. And just going to walk through it. It's a single linear path algorithm. It's quite nice. Okay. All right. So we're going to either 11 or 12 or 25. 12 goes to either 13 or 27. Strut. Who cares about planar? And then 13, right, goes all the way down to 16. Which point it either goes to 17 or to 21. Right. And then 17 down to 20. Which point it then goes always to 11. One down to 24, at which point it always goes to 11. (25 to 26, where it just exits stage left. Not going to worry about where that goes. And 27 to 28, second verse, same as the first. Right? So you basically just walk straight through it, and every instruction is going to be allocated to some particular basic block. Right? Every control decision, very clear, right? You can pick out structure from this, right? Again, if I draw this a little more cleanly, you can still see the if-else. Right? The loop here is a little wonky because it sort of played out in 2D space more than 1D. Right? But you can reconstruct and understand program behavior and think about what this is going to mean. Right? Again, why do we care about program dependence graphs? Because they're going to change what we can and cannot exploit. Right? Right? If I don't really have good branch prediction and I want to do something about this, maybe I throw some predication at it. Now, if I am looking for what I could try to find more ILP in, right, I need to find where my loop body is to unroll it. If I do not understand what my code is doing, it is very difficult to optimize it. It is difficult to reason about how amenable it might be to any given optimization. All right. Any questions about basic blocks? Single entry, single exit. Find them with a nice, straightforward linear path. You want to draw the graph, you draw the graph. All right. Okay. So, data flow. I didn't draw all of the arrows. I just wrote them all out. Mostly because I find that if I draw all the arrows there, it starts to look like a Jackson Pollock, and it's a little hard to read. But now we don't need to fit that whole thing on the screen. Let's get bigger again. Okay, hopefully that is better in the back now. Okay. So, how do you do each of these? Well, each of these is a linear pass. Right? So if I want to do read after write, how do I want to do that? I'm going to find the first instruction. I'm going instruction by instruction, and I'm going to look for what does it define. Right? this defines register 7. Okay, great. I'm going to walk through this and find every use of register 7 until such a time as register 7 is renamed, is redefined by somebody else, or I've run out of instructions. So register 7 is defined in 1. It is used in instruction 4, and that's it. Okay, great. Move to next instruction. This defines register 3. I walk through and I say, where is register 3 used? Well, you're used in instruction 4. But you're also being redefined there. So I'll stop the walk there and move on. Okay, so good 4, register 3. I can look at register 6, right? And say register 6 are used again. No. Okay. So now I get down to register 4. Well, you're defining register 3. Is this version of register 3 used subsequently? Yes, it is used in the store word. Write that down. Store word does not define anything. It defines memory location. We're just talking about register carried dependencies. Load word defines register 4. Branch uses it. There we go. Single pass, straight on through. These are your read after write data dependencies. The real ones, the producer consumer relationships without which your program literally does not work. Right? These are scheduling dependencies. Write after read, write after write. How do you do those? Simple. You just start from the bottom. Right? So say you want to write after write. You find something that writes something. You wrote register 4. Does anyone else write it? Nope. Okay. You wrote register 3. Did someone else write it? Yes. So then, therefore, 4 must come after 2. Otherwise, the value of register 3 that is being used would be wrong. Scheduling constraint. You do the same for write after read, right? So I'm going to say, okay, find everything that's written and walk backwards through all the uses. So this defines 4, this reads 4. They must be ordered thusly, right? Do that for each of them. Okay. Again, if there is a redefinition, right, you would stop. So if there was some definition here of, say, register 3, right, and you're walking backwards, then you would stop your walk in this instruction. This is exactly the same as the previous, so I will leave it as an exercise for citation, should you so wish. This is drawing the basic block graph. It's a little smaller, so I'll do this one more time. Maybe we can get something a little more eye-pleasing. Probably do, but I'm just going to erase this. Okay. So I'm going to walk through this a little faster. Okay. So we have, start at the top. Let's do this all in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 25 instructions. Think ahead. Oh, 25 wasn't that important anyway. We'll draw that off the end. Okay, so we're just going to start drawing down. So instructions 1 and 2, we start at a label, we end at a control instruction. This is our control instruction. Where does it go? It goes to either 4 or 3. You can go to 3. You can go to 4. Means 3 is register out to, we'll collect that one later. So let's just leave that dangling for the moment. Okay, 3 does not go to 4. So starting anyone here. And 4 goes to 5, which goes either to 6 or to, where is Capybara? 7. Okay. 6, yeah, 6 is its own little isolated piece. Okay. And 7 is a nice run here, 7 all the way down to 13. Again, we'll deal with where these are going in a second. We'll fix those. Or just get the basic blocks themselves right, and then we'll fix the rest of the graph. Okay, 14 down to 20. Okay, again, this one, link. Okay, and then 21 down to the end. So not a whole lot of basic blocks in this program. Now, where do these go? So there are two places that this return could go. Actually, sorry, three places where it could go. It could go to either the two places it was called from within it, or it could go to somewhere externally. So if you're looking for the set of places this link could go, all right, this is either going to, what are the numbers here? 14, return from this call, 20, return from that call, or it could be going, 21, return from that call. Or it could be going to the original caller, right? Okay, same is going to be true here, right? So this actually has the same set of possible places it could be going, right? It could be going to 14, 21, or the original caller. These, however, the recursive calls themselves. Sorry, that's this one. These actually are well defined. They go to back to 1. Right, so let's draw them. Play. So any questions about how we did that? Right, the basic block formation, same as it was before. Walk through. Straight line instructions stay in the same block. Labels, begin a new block. Branches, go to multiple blocks. The only interesting thing we have here is, right, jump and link is still just like a jump. I know exactly where it goes. A simple, well-defined arc. Jump register, it's a computed jump. I have to look at all these set of places it might be going, right? So this could be going to any of the places it has been called. 2 of them are in this program, 1 of them is external, right? 1 of them is not given. But you'll note, you read the instructions, it does tell you what to do to return to the original caller. Okay. Again, this is the same as before, nothing interesting there. Okay, so now we get into our deja vu section. So note that, let me talk about what I'm interested in people knowing here. You have to know how this part works in the baseline. Yes. If there was something that was calling some unknown piece of code, I would give you explicit instructions on how to handle it. Yeah. And if there's anything that appears ambiguous, please ask during the exam. We're not trying to drive you off into the hinterland. We're trying to give you things that are actually, in this case, a well-defined piece of code that does something. Well, tree search, right? So, but no, we would not be trying to give you a bunch of out-of-scope stuff. But the caller of the function itself, if there's a return, is never going to be there, right? So, yeah. Any other questions? Okay, so let's ask why we're bothering to ask a 331 question on this practice exam. We fiddled around with the pipeline a little bit at an extra stage, but doesn't really do too much. So again, this is really more about in order to understand the relationship between our VLIW and our superscalar in order machines and what they were trying to improve upon. You do have to remember how the baseline works, right? Speed up always has a T old, right? If you can't figure out what T old was, then you don't know whether or not T new is good, right? Also, I do want to beat it into your head that there is nothing magical and special about a 5-stage pipeline, right? It was what was a good decision for the original MIPS folks in 1986. but there's nothing magical about 5 stages. Okay, so if you can generalize, remember how these things play out, then you could look at the same piece of code, right, on a scalar in order pipeline and the same piece of code again, and look at some of the differences in how it gets scheduled when you move to VLIW or superscalar in order. Okay, so this should be basically review. Now let's start here. Does anyone have any questions about why, for instance, the forwarding we're seeing is shown where it is? And here I've shown that you actually have 3 different options for when this forwarding could even occur. Right? All of these are actually equally valid. You have not been told enough about the pipeline forwarding internals to know which of these cycles this happened with. Any of these would be a perfectly reasonable answer. Right? A large design space of possible implementations you could be looking at. Okay, so load into 2. I have a consume that is happening here, right? Add into register 5, consume that is happening here, right? Load into 3, nothing uses it. Oh, sorry, load into 3 that's used here. Load into, add into 2 is used in the store word consumes late, and then load into 4 used in the branch, right? So always worthwhile if you are pondering such things to figure out which of these things are actually dependent. If they're all independent, it's very simple, right? Take the repeating pattern, just write it repeatedly on the page. If they are dependent, figure out where the dependencies are. Those are the only places you'll have stalls. Stalls occur because of dependency. Okay. Questions about this schedule? Does anyone have any questions about this particular schedule? Seems good. We'll look at later. We'll print it out. Groovy. Okay. This, I think, is a somewhat more interesting question, right? To go backwards. Okay. But again, as I said, review is good. It's worthwhile, to know how things go forward, but before you try to do them backwards. Nomine patre. Okay. Right. So all you really care about here are the dependencies. Right? The rest of this is irrelevant. So if there were stalls, there were dependencies. Everything else could be anything. It's not constrained. So I'm going to look at this schedule. I'm going to say, I stalled. So I must have needed something that this load word was producing. Okay. Now, my load word takes 2 operands. One of them is immediate. I can't need the immediate. I must need the base register. When do I need the base register? I need the base register in my execute stage so I can add it to the immediate. So yeah, that's what I was dependent on. Boom. Okay. Do the same logic here. I have another load. Also going to be dependent, right? And the only thing it could actually still be waiting for at this time, right, would be this load, right? It can't be waiting for data from here. That data was already available at the time it was decoding. It wouldn't have stalled. So it must be waiting for data from here. Same thing here. I have a subtract. Right? I know I'm dependent on that immediately preceding load, right? And logic goes on. Now here, right, these 2 are independent. There's no relationship between them. Could be, could be anything. Okay. Now the load and the store are interesting because here, I know that they're dependent because they stalled, but how do I know which of the operands it was dependent on? Well, that's because they behave very differently. I need my base address in execute. I need my value to store into memory in you only got 5 stages. You got 20% chance of being right guessing anything. When do I need the value to store into memory? In the memory stage, right? If I have a load followed by a store, and I'm loading a value into a register and then storing it right back. So it's like doing a mem copy. I loaded from one location, I'm storing it back somewhere else. If it's a value that I loaded that I'm dependent on to store into memory, I will not stall. Right? And if I just need the value is ready here. I would need the value here. I'm good. No stall. So I must be dependent on the address. Right? The only thing that the store could be stalling on is the address, not the value. Right? Because the value would be available when I needed it. Okay, so again, let's go over the basics. Right. So the earliest that I need any operand, what instruction has the earliest need for an operand? What class of instructions needs an operand earliest? What instruction is the last instruction on the screen? Branches, right? Our branches need the operands earliest. They consume operands, right, in decode unless told otherwise, right? Even here, again, we do explicitly tell you, right, when it needs its data, right? So if we tell you that there is, branch resolution in D, then clearly to resolve my branch, I must have actually had the actual value. I need my operands in D. Right? Also argue that like jump register also needs that there, but it doesn't. They're not a common enough instruction for us to care. Okay. So what about the other instructions? What about any ALU op? When do I need my operands? Which is going to produce a register value. So when do I need my operands for an ALU operation? Yeah. Right. And even if I have a 5-stage pipeline from execute, I need them in the first of these stages, right? And whenever the execute begins. Right? Okay. When do I have a value available? Again, let's start with our standard. Right. When is my value available from an ALU op? Because they do produce values. It's a value available in M. Right? When I'm done with execute, it is available. Right? It is not available while I'm doing it. Right? You can't eat the sandwich while I am slicing it. Very much not recommended. OSHA does not comply. Right? You have to wait for me to finish making the sandwich. Okay. And you can eat it. Okay. Load. Right? Needs all of its values in execute because while it's computing the effective address, its value is not available until write back, right? Until it is done with memory. Store has multiple answers here, right? Store needs its address data in X, and it needs its value in M, and produces nothing. Okay. If I have branches, load, stores, and stuff that does stuff, it's basically all your instructions. All right, these are all the ones that we really care about scheduling. Are there some other instructions? Sure. Not going to really worry about them too much. Okay. I guess I shouldn't have done X as a stage here. Let me do a there. Now it's unambiguous. Null. Okay, let's look at the other question that we ask here. Is there a branch predictor and did it work? How would you know? How would I know if there's a branch predictor? If I did not have a branch predictor and I was resolving this branch au natural, right? When would I have fetched foo? Right? My branch resolves here. Right? This is when I correctly figure out which way I did or did not branch. When D completes. So if I didn't have a branch predictor, right, then I can't possibly have predicted that I would go backwards. I'd have to go forwards. I don't have a branch predictor. And I could not actually initiate that fetch until cycle 15. So clearly, there is a branch predictor, right? Because I started fetching for this location before I knew that I needed to do so. I don't know if it was right. Well, it didn't destroy the instructions that it fetched, so it must have been right. Didn't squash them. Right? Some of these questions aren't intended to be, hard. Okay. Any questions on how we knew there was a branch predictor? Didn't squash, it must have been correct. Great. Okay, second part of that should be appropriately trivial. Okay. Yeah, this is basically second verse, same as the first. So if there were no questions on the previous, we'll move on to the concept questions. Okay. List two limitations of super pipelining. The answer is not kryptonite or lead. Okay. Super pipelining, recall, is chopping up your stages purely for the purpose of making them faster, not because you're separating logical function. Right? I just want to make that clock frequency as high as possible, make my marketing people very, very happy that the consumers only need to know one scalar value to compare their processors, right? Et cetera, and go home without any understanding whether it was actually any good. Now, to take advantage of technology, you are going to do some degree of super pipelining. Again, as I mentioned, the 6-stage Niagara was insufficiently bold, right? And that hurt it quite a bit. But on the other side of it, the 50-stage net burst architecture was perhaps digging too deep in the frequency mines of Moria. So what are the things that are going to be the back pressures here? So my pipeline loop lengths increase. Right. So again, your pipeline is not all feed forward. There are these backward edges. The further apart the beginning and end of that backwards edge get, the more that hazards will become visible in your pipeline. Right. The dependencies are naturally in your program. They're not necessarily hazards, right? If they don't get stuck in those loops, they're fine. There are some non-scaling delays. Super pipelining does nothing for your DRAM. Right. The super pipelining, my eyes, the super pipelining does nothing at all. Here we go. 20-year-old Simpsons reference, right? Okay. Increasing overhead to work ratio, right? Your pipeline registers themselves have some delay, they have some cost, right? They don't actually do anything other than hold state, right? So again, I only need two. I'm listing several. Right? So at some point, your pipeline stage is basically just, latching and unlatching, and you're not really doing any work. So that's not a great way to build a machine. Some stages just don't divide well, right? It's pretty easy to understand how I arbitrarily pipeline an adder, right? Again, think about the world's dumbest, simplest adder, a ripple carry adder, and I can pipeline it without loss of generality, certainly all the way down to a single full adder cell per cycle, right? It would be very logical how it would keep initiating things every cycle. It pipelines very naturally. Try to do that to your cache lookup, and you will run into some other challenges. In particular, when you start worrying about whether or not you can pipeline a wire, you have gone too far. And yes, sometimes you do actually have to pipeline a wire because it takes time to charge. Okay. Hazard checking and forwarding do not scale as a function of the number of pipeline stages. Right? So if I have, it was not an in-order machine, but if I have 50 pipeline stages after my point where I do want to do my hazard checking, right? Well, good luck actually figuring out whether or not any of these future things even actually produces the value you're looking for. The techniques we have discussed do not scale to arbitrarily deep pipelines very well, right? Certainly not linear. Okay, two properties common to RISC ISAs allow for ease of pipelining. Again, the alternative name for RISC rather than reduced instruction set was regular instruction set. So whether you say regularity of resource usage, regularity of instruction format, right? These are all things that are pretty straightforward there. Avoiding implicit state updates, no weird side effects. I only have one type of data that I am trying to update with any given instruction, which means there's only one stage in the machine that I am actually changing the globally visible state, which makes me not have to worry about things like write after read hazards within my pipeline. Okay. Let's talk about a pure VLIW machine versus a scalar design. So imagine I had an exposed pipeline, but with width 1. So like VLIW width 1. So very not particularly long, instruction word, right? So again, imagine a miniature giant space hamster. Oh, for the eyes, boo. Okay. And you say, what would this still make any sense at all? Just really let the compiler try to solve your scheduling for you. And the answer is, well, some, right? So even if you weren't going wide, right, exposing the pipeline, exposed microarchitectures in general would allow you to build a machine that doesn't do a bunch of checks, and you could actually scale, really, 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 really deep and let the compiler do all the work for you, right? Is it probably a good idea for anything other than some very, very niche applications? No. Probably gonna have poor CPI. So even if you can crank the frequency up, it's not clear how much you got. It doesn't support caches. Remember, pure VLIW, the compiler had to predict everything, including whether or not your load is a hit or not. So it doesn't have caches, it has scratch pads and explicit memory transfers, right? No branch prediction, no backwards compatibility, low code density. But the other thing that you do get here, and why you do see some of these things, I mean, again, not one wide, but again, pick out the useful points. If you look at the place where VLIW is still in practice in DSP, decision signal processing, one of the nice things that those things have to deal with, or well, not nice, one of the affinities of VLIW to that is if you're letting the compiler do it, the compiler is doing this worst case analysis. Well, guess what? If you have a real-time system, right, worst case analysis is actually mostly what you're concerned with. I don't care about my best case performance, right? I care about whether or not it actually hits, whatever hertz it needs to be doing to correctly implement a protocol, to have whatever structural guarantees that it needed to have for fault detection, et cetera. So if the compiler tells me, well, in the worst case, this hits 60 hertz and needs to run at 60 hertz, you're like, perfect. I don't want variability. Variability is bad. All right. So, okay. Okay. So predication in scalar versus superscalar. So this is just reminding you what the costs of predication are. So in predication, I have to do both sides of a branch essentially, right? If I have a superscalar machine, I've got parallel hardware and I can't utilize it unless I can find an independence. It's usually actually underutilized. So the effective load on my machine that could bog things down, I've got space to put those extra instructions probably, right? If I have a scalar machine and I'm doing both sides of a branch, I'm doing a lot more work and I'm going to see all that latency. So unless both sides of a branch is like one instruction long, right, it's probably not a great idea on a machine that can't actually pay off that extra work with by filling in the width of otherwise underutilized functional units. Okay. Okay, leave this one as an exercise to the reader. A little bit interesting, but it's not, there's a bigger space of discussion, so I'm not going to go into it right now. Okay, let's do VLIW. Okay, so this is a little more tedious than what you would see on the exam, right? A 3x loop unroll isn't hard, it's just take you a little while. So here we have a machine. It does not have any hazard detection for anything other than the W2D bypass, right? It only supports W2D forwarding. Everything else you had to schedule, right? So how's this going to work? Right. Let's again make this a little smaller. So if I want to loop unroll this, then first think about loop unrolling. There's the work that needs to be done. There's the update that needs to be done. And then there is the branch itself. And no matter how many times I unroll it, there will ultimately be one branch. To the degree that I can amortize the work to be done, I will do it only once per loop as well. right? And then the main body of the work is going to be replicated. So you can break this down, this loop here. You can see these are the updates of the pointers, right? So I can update them once with 3 increments worth so here again, you're going from an I++ to an I plus equal 3, right? You're going to go from a +4 to a +12, right? But you're going to need, instead of 2 loads, you're going to need 6. Instead of 1 addo, you're going to need 3. Instead of 1 store word, you're going to need 3. And so what you can think about doing is I can start by even just scheduling that first loop. I do these 2 loads, right? I take that first instruction. This is as early as it can go. This one's independent. That's as early as it can go. Great. When is the earliest in this machine that I could possibly do that add if I only have WD forwarding, right? Well, these are already here. So this is the earliest I could schedule this add, right? If this add produces a value that's needed by the store word, what is the earliest that I could schedule, right? The relevant store word, right? Work through thusly. And we're not going to test you this much on actually doing the loop unrolling, but it's still a worthwhile exercise in your time to see how it's going to play out, right? The other thing you'll notice here that we had to do, right, is I can't just go load word 2.3, load word 2.3, load word 2.3. I need new names for my registers. Why did I choose 12 and 22? Because it was easy to type with 1 extra character. There's no deeper meaning here to incrementing by 10, right? All right, so you can see that these are 2 and 3 that are seen by here, used, consumed, etc. Okay. So the nice thing you'll see here is think about just doing 1 iteration of this. Right? Ignore all the rest of this. I think about the rest of the schedule is going to mostly sort of play out pretty similarly if I delete these other 2 iterations, right? Because this is actually still the earliest I can do this add. So I'd have a pair of no ops, right? This is the earliest I could do, right? This store, right? So I'd have a pair of no ops. Well, not necessarily. I could do my increments, right? But there are going to be a couple of instructions in between there. That's the earliest I can do my branch, based on this path here, right? So this actually doesn't get, in this particular case at least, longer for want of doing the extra work, right? So you can see the appeal here when you're trying to fill in all these slots, right? I have a lot less than 3 times as many bundles, right? I'm filling in that extra work. Okay. But again, you are not compilers, so don't worry that you're going to have to make something quite this pretty on demand in 10 minutes. You will be given more structure. Yes? So this is a dependence distance issue. So these store words are independent, right? It's not data dependence between them. But this store word depends on register 2 computed here. This one on 12 computed here. This one on 22 computed here. This is as close as they can actually be. Yeah. Yeah, if I had more forwarding, I could pack it a little further. This is a machine that the hardware for this is very simple, right? For this is very simple, right? But that also means that the compiler's job gets more complex. So you see the same thing actually sort of play out here. So here is a schedule, as you can see, full of no ops. Right, same sort of setup. You can see the forwarding actually happening here. Here the actual dependence is playing out. And even if you go and say, look, I want to actually do hardware detection for this, if it's still the I'm still stuck with this forwarding model, it doesn't actually get particularly better, right, from a scheduling perspective. Less code, right? But all those no ops, we're just doing sort of the same thing that hardware is doing, right? So what I really want to show you between these 2 is looking at the duality of whether hardware is doing the scheduling or software is doing the scheduling. The dependencies are just whatever they are, right? So save some code, but We won't do anything particularly interesting in terms of speed up. Okay. Leave that one for and move on here. Okay. Okay, so how does superscalar in order work? Well, a lot like scalar in order, right? Just you're going to do k things at once, right? So here we have a set of instructions. Again, these are independent instructions. These are not bundles. I'm going to be fetching multiple of them at once, but they're just scalar instructions, right? So the beauty of superscalar in order, right, is that it has full binary backwards compatibility. You can feed it, whatever set of instructions, it will determine whether or not parallelism exists, right? Okay, so this is going to be a two-eyed machine. We've got two of everything. Do you actually want two of everything in a two-eyed machine? No, that's a different question, right? But it makes this problem nice and simple. You don't have to think about it too much. We're going to fetch two things, right? So far, nothing could go wrong, right? We haven't even figured out what the instructions are yet. We can't possibly have any stalls. We decode both of them, and hooray, it happens that these two particular instructions that we fetched are independent with respect to each other. They might not be. They're two arbitrary scalar instructions. They could be dependent with each other, right? The compiler didn't do anything to guarantee that. Since they happen to be independent, we'll send them both down the pipe, right? And again, just as with your, your standard scalar, right? Once they reach past the end of the hazard detection, or you can just fill in the rest of the cells immediately, right? There are no further stalls that are going to occur. Okay, so those are now scheduled. What about things coming in behind it? So here we decode them and go, oh, well, actually, these are dependent on things both on each other and things further down the pipe. For older instructions in the pipeline. So the good news, it'll turn out if you look at these two, even if I'm scheduling these in the same cycle, forwarding can actually resolve my internal dependencies between these two. So that's fine. But I do need to wait until this value and this value are both ready. I can't send my add down until I know that it's actually going to be ready. When's it going to be ready? Well, it's a pair of load words. They'll both be ready here in cycle 5. Now, since these stalled, all of these stalled behind it, right? So we've not discovered anything new. We're going with our nice simple lockstep scheduling, i.e. the simplest way to build it. So we're not going to have to worry about advancement across stages between cycles. So we go to the next cycle and we say, okay, you good? Like, yeah, I'm totally going to be able to forward those values. Life's going to be fine. I know in cycle 5, I'm going to be able to forward the register 2 and register 3 values I need. I know in cycle 6, I'm going to be able to forward internally the register 2 value that I need. Go down the pipe and be productive. Execute some code. Okay. So decode succeeds. So fetch succeeds. Next cycle, we're going to barely go along. Decode. Great. I look at both those instructions. So yeah, you're completely independent of each other. And register 4 was last defined, well, whenever the last time this executed, it's a long time ago. Right? Register 5, same deal. So off you go. The race is with you. I go to next, and I fetch 2 instructions because I always fetch 2 instructions. I don't know what they are yet. Right? So I'm going to fetch a branch. I'm going to fetch a no-op. Right? And you can look at how you want to draw out the squashing for some of this later, but we'll come back to that in a second. I'm not, super worried about exactly how you want to represent it. It doesn't really matter in this particular case. But we'll get to that in a second. I'll fix it up nicely for the final version of this. So here I go to do a decode and go, oh, well, I'm not ready to go. The branch needs this value. I don't have my value. But we assume that we have a predictor, and the predictor is always right. So I will actually start fetching here again. And you get the loops playing out across the pipeline. Right? So once you get one loop scheduled, in steady state, it's just going to keep doing the same thing over and over again. You can see that, in fact, what you're actually getting here is every 7 cycles, right? You reach the same state you're in before. So in 7 cycles, we do 1, 2, 3, 4, 5, 6, 7 actually useful instructions. That does not count, right? So yeah, it's a CPI of 1 with a 2-eyed machine. Yeah, it's not too bad in the grand scheme of things. Okay. But we're gonna have to wait here until we actually get this branch resolved, validate that in fact it was actually taken, and then everything else frees up and plays out behind it. Okay. Now, at this point here, right, I could decide that this is actually after a branch I'm predicting and squash it. You could actually get rid of a pattern that looks F dash 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 dash, right? That'd be perfectly valid too. It's already a no-op, so what would actually happen is you'd turn it into a no-op. So 6 of one, half dozen of the other. If this was actually some actual other particular instruction, you would probably want to at least make sure that you wrote it as a dash. I'll clean it up in post. Okay. Now, the good news with loops is that they loop, right? So once you get to this point here, right? Once you've gotten to cycle 11, you can schedule the rest of this with some copy paste, right? You don't need to rethink all of the same problems all over again. Right? It's just going to repeat. Because I know what the dependencies are. I know what the stalls are that it causes. There's no shift in my schedule. Nothing has changed. Right? If I end up in the same state, I'll exhibit exactly the same dependencies turning into hazards again. Okay. And again, you can, have a more test-friendly version of this that cuts off at, say, cycle 11. Okay, FGMT. Let's go very briefly here. So fine-grained multi-threading interleaves other threads because work from other threads is always independent. There might be structural hazards, right, if something is occupying a non-pipeline unit, but other than that, right, you're good to go. Right, so if I do have something using my one divider, it's not pipelined, and something else comes down the pipe and also tries to use the same divider, yes, you could get some hazards. But again, did you see divide over there? No. Why? Because divide almost never happens. We're not dividers, we're uniters. Okay. At least we like reduction operations. Okay. So what we're doing with these additional threads is hiding our dependence distances, right? That is the reason we're doing FGMT. It is not to improve the latency of any given thread. It is to improve the throughput of the machine, is to keep the resources utilized. So you can say, okay, well, what is it that I'm actually worried about here? How many additional threads would I need to hide all the stalls that I'm seeing? Well, you ask the question, well, how many stalls are you seeing? Well, my longest distance here is 2 stalls worth of work. So certainly, if I had, now you can say, well, what would happen if I had 1 thread? Well, if I had 1 thread, it'd be this from me, something else from someone else, something else from me again. I'd still be stalling. Not good enough. I have 2 stalls. I'm going to need 2 threads to cover it. Okay. Then you can also ask, in this particular pipeline, what is the worst case stall you could have? Well, it actually also turns out to only be 2 stalls, right? W to D. I need something in D. It's not being produced until W from the immediately preceding bundle. Fetch bundle. So if I have at least 3 threads, I'm good to go in this particular 5-stage pipeline. Right? So in particular, say if I had a more friendly number of threads, like 4, again, your schedulers like powers of 2, right? Then I am definitely covering all of the simple data dependent stalls that you would see from production consumer aspects. Now, if I want to cover my L1 cache misses, is 4 threads going to be enough? No. If I had a more technology appropriate pipeline where maybe L1 cache hits or even 3 or 4 cycles, is 4 threads going to be enough? No. But for what's given, right? If I want to know how many will fix this particular schedule, if these are the only code in the world I ever care about running is just this loop. me and my loop, right? Off in a cabin in the woods, from now until eternity. I need 2 more threads, right? And if I want to look at generalizing this to any sort of pipeline, longest stall distance in terms of number of stalls I could have, cover that with that many threads, and you're definitely good to go, right? Now, could you actually get a number that's smaller than this? Actually, also yes, but I'm not asking about that particularly. I just want you to understand what FGMT is for. And I will, as I said, put up another couple of FGMT questions. Okay, now, before we go to this one, I want to talk to you about why this is even here. So this is a 16-point problem in a, 10-point section. So this is some signaling that this problem will not be on your exam. Right? This problem is substantially harder than anything that would be on your exam. You can ask, why is it here? Right? I didn't even bother finishing beyond cycle 14 here. But what I want you to understand from this problem is actually the following. So I'll be quite explicit. I want you to understand why we are still operating with our toy 5-stage pipeline, why we are still, to use your standard physics mechanics, nomenclature, living in a world of spherical cows, homogeneously filled with milk, floating in frictionless vacuums, because anything else that you would actually start to do to model a real machine gets really complicated really fast, right? So even if I've just basically added a decoupling queue, right, you can already see fun stuff starts to happen. If I actually look at the limitations of this visualization format, right, if I'm starting to fetch 4 wide, I will wrap around and have, as you can see, at this point here, 3 copies of this instruction are in the pipeline at the same time, right? It's not, right? Real things are complicated. And if you saw that ARM-A8, real things have queues, right? Real things have all sorts of other funky components. So will you be tested on this? No. So you will not be tested on this. Do I think it's a good intellectual exercise? You at least think about all the ways that your pipeline could start changing, even in just a simple superscalar in-order machine. If you want to think about what you need to understand to go build or analyze a real one, yes. Should you study this? After everything else has been studied, in your copious free time. But I do like to help occasionally try to calibrate us versus the real world problems. We're not living completely in toyland, right? Okay, so moving along, these parts are definitely in scope, okay? So if I have an n-wide superscalar in-order pipeline with k stages after hazard detection, or a MIPS or MIPS-like ISA, how many read after write dependencies and how many write after write dependencies need to be checked in the hazard detection stage, right? So the total number of things I'm going to need to check is going to be the number of intracycle plus downstream, right? We've been told there are k downstream stages. Cool, right? And intracycle, we know that there are n in each cycle. So if you even just start to look at just the downstream portion, right? So 2 operands per instruction that I need to check against. So everything that's currently in my hazard detection stage could have 2 inputs, right? Then there are n such instructions that are in hazard detection in the worst case in my n-wide pipeline. There are k possible locations further down the pipeline that could be generating something I might need, right? And there are n instructions potentially in each of these k possible locations, right? So just the downstream read after write alone already gets you 2kn. Doing out the rest of these, I do leave that as an exercise to the reader in the interest of time since it's 10:17. I'll go through these last 3 here. Why might a 4-wide superscalar in-order pipeline have less than 4 copies of a functional unit? List 2 reasons. You can phrase it in a lot of different ways, but basically it's either asymmetric usage or asymmetric cost, right? If I only use it 3% of the time, right, why on earth am I building more of them, right? I'm probably not going to actually use it. if it costs 10 times as much as any other thing that I could be adding another copy of, I am going to probably not scale with n. Right? Even if I use it all the time. The classic example here is load ports. Right? Load ports are useful. 20, 30% of my instructions are loads. They're just really, really expensive. Right? An extra load port, I might as well almost build another cache. Right? They're very expensive. Right? So I just can't afford it. Okay. Cost or benefit. Right? Pick one. Pick both. Advantages and disadvantages of statically scalar superscalar versus pure VLAW. Again, compatibility, variation tolerance. These are nice things that the statically scalar gets. Disadvantages, we just saw quadratic forwarding. So not having to check for all these things would be great from a hardware perspective. Making the compiler give you a schedule that doesn't have to check for these things, not so great necessarily for the actual execution you're seeing, right? Non-deterministic performance is also something you will get with your statically scheduled superscalar designs. So again, if I want to do worst case analysis for a pure VLAW design, it's already been done. Right, that schedule already is my worst case. That is my schedule. My schedule is my schedule is my schedule is my schedule. Right, it will run at exactly the rate that I expect it to. Right, pure VLAW doesn't have cache message. Doesn't have. Right. Whereas statically superscalar, you actually have to do quite a bit of analysis to try to figure out, well, what is my worst case execution time? Right? How do I know? Right, the hardware is going to figure it out dynamically based on whatever code pattern I'm seeing. And again, another question on predication, like when would it actually be worse than just flushing and re-executing, right? So even if you had a branch predictor, there's always, always missing. Another thing you want to understand here is that predication is only generally considered useful if the two different paths that you were walking down and doing both sides of are about the same length. Again, think about the degenerate case. If on one branch of your if then else, I do +1, and on the other branch of the if then else, I solve a traveling salesman problem, I probably don't want to try to use predication to get rid of that branch. One of these things is not like the other one. Okay, it is 10:20. I will see you all on Tuesday. And again, the answers to all of these will be out on Friday. And there'll be some online quizzes, which will be not graded, but will allow you to self-grade yourself as to whether or not you're ready to answer some of these questions. Have fun.